Hello, welcome to another video here at TURBIVAP. Today I wanted to address a topic and discuss it with you here. A little about solid particle erosion in turbines. Steam, more specifically from an exclusive point of view. They're a static element in the expander, an injector or, in this case here, speaking of the diaphragm. So let's understand a little better about this subject, this erosion. A serious problem for those who operate the turbine, for those who are in charge and already know. What is? Nothing but small particles, regardless of origin. And generally boiler piping handling. Any intervention that is made on the network and micro projects are designed. Segments and pieces of electrode materials and sludge. Anything that is smaller than the vapor filter there, it ends up entering the turbine. Then we will understand a little more about this phenomenon, not what it is actually about, okay. I won't go into details about diaphragm, none of that, but just a little more curiosity about the size and influence of the size of this compound and the type of wear it provides. Which region specifically there, of the diaphragm block. There are studies that correlate up to 5% efficiency losses, depending on how worn this profile and the diaphragm block are. Because as I'm going to show you here, we're going to go to the screen. We will see that here is a view of the diaphragm block exit. Okay, we are looking here at the exit view where it will meet the steam. It's coming out here. It's finding it here in the monitor plane here. Another rotor blade, the movable blade. So he will find an optimal angle of incidence there, optimized to generate torque in the rotor. So, if we look here, there are two cases. The first one here shows a very characteristic degradation. This contour here, this wear here, already causes a lot of turbulence. It reduces efficiency. Why? Because it ends up projecting vapor that is no longer in the direction. For that triangle of speeds there that we who study turbomachines know. He ends up distorting that, so it does not project the blade at the optimum angle of incidence. For the reed, the steam. So it ends up causing a disturbance, an inefficiency. Imagine you are making a lever and a lever force at a point that is not the most appropriate. So we're losing mechanical effort and everything else. So, this causes the turbine's efficiency to drop. And here is another type of phenomenon that he is degrading here. Already in other regions, we're going to see a little more detail, even for whom. Just to give you some context, for those who don't quite understand. I'm talking exactly about this profile here. Here's the diaphragm. This is a model, there are several. Here is more illustrative. Is it an inner or outer ring? It is attached here to the housing here by an internal ring. Usually here comes the sealing element, the labyrinth ring. We are talking about here, where the steam is passing here. It comes from this direction from left here to right, and then it will be shaped here inside this piece. So he's the one who comes here. Oops, so he's the one who comes here, right? Each disc here has the diaphragm position. The steam expands, meets the wheel, and generates a torque movement. Here in the circle, so it's this guy. Okay, so let's understand. He has this characteristic profile. The steam is coming from top to bottom. In this case it will be compressed. There is a passage restriction here, so he increases his speed. In this second, the thermodynamic principles decreases the pressure, but there is a gain in speed. So imagine the steam is coming here. It has the steam lines, tends to flow. There is a pressure zone here and a suction zone. And in this pressure zone, depending on how this solid particulate enters on the machine, which is what I'm going to go into detail about, what he causes, what kind of wear phenomenon does it cause? Okay, so, a study was done here, a modeling, with more than 540,000 points, to arrive at a very interesting result. And then we start to do some analysis in relation to the results, what is being proposed. So here he is doing a simulation. And here are the lines as if they were bodies, that is, small solid particles with a size greater than 5 microns. Then by how he behaves. And here it would be entering there, entering the machine along with the steam. So each little line here is showing a streamline. It shows us what is happening with this vapor's behavior, with the solid particles. So, notice, as expected, he enters the profile here. Due to thermodynamics, it will tend to vapor and the fluid will tend to conform and flow exactly according to the profile expected by him. So with a 5-micron particle, it will basically follow the expected path closely, which is the steam path. Already with a solid particle, here at 20 microns, we are already starting to see times the shortening of this profile, that is, we are already starting to have an inertia specific to this particulate, so it will find itself here, and will tend to have different behavior. So he will already have a, let's say, a kind of life of his own. Then he will want to flow already in another, and another sense, with different vectors here. And here we can see a narrowing here in this layer, a greater direction here, to that region there, from the same point of view of 40 micros. So what would happen to the body going into that situation then? He has completely lost his fluidity. The vectors he no longer has to follow the steam. It has a higher incidence here in this region and also for 80 microns. So here would be the visual study on top of these vectors. Here we have another graph showing the speed of this impact in meters per second, and here the diameter of this solid particulate in microns. So we notice that the bigger this is, particulate, and here it is an inclination, an angle of incidence. So when he is very short, particulate here around 5 here more or less, and has almost no angle of incidence, it deviates far from the expected profile that we saw there in the lines. As we increase the size of this particulate, it tends to have an inertia that is reflected in the change in curvature. Then he starts acting on an angle, and it's the same with speed. What happens there is that we have an angle of incidence. So let's look at the 5 micros again. He tends to have little ones here and here. The little red dots, they are the erosion zones. So, the greater the erosion, that is, those little holes that you see on the surface of the larger piece, and the redder they are, the more dots. Is larger, deeper, larger, and damages the part more. So, with 5 micros here you have it. We can see the pressure zone very little, already here at 20 microns. We already begin to see an accentuation here, a location already further outside the block's exit edge, but here in a smaller region, here with 40 micros, quite evident, and with 80 here, and visually, it seems to be smaller, right? Because it's less red. However, it starts to get much more denting, then evidenced here by other colors. So it starts to have an increase in crushing, as if it were perhaps here, even the worst view, right? So the smaller it is, the closer to the trailing edge. Here he did another simulation, only with larger, even particulate elements. Solid of 200, 300, 400 and 500 microns. And then 200. What happens, right? 300,400,500. So, basically they are bigger shocks. And then the result of that is in this graph that we have here. On this axis it would be as if it were the loss of material resulting from this erosion, caused by solid particles, by erosion. And on this axis here we have the distance. So here is the steam inlet region, and here is the general outlet of the steam closest to 1. It's exactly here at 0.7 to 0.8 here. Here we have the trailing edge of the diaphragm, where the steam actually comes out. So we want to escape from that region, and then he shows it to us here. The diaphragm pitch. So, when we vary, we oscillate there. The step, the smaller it is in this case here, the more we run away from that critical zone, which is the block's exit in the diaphragm. So that's the main conclusion. And here he shows some coatings for application to the diaphragm block. Some materials, and here are the alloys and how much they would withstand of erosion in hours. How much more resistant are they? And then the explanation for useful life depends on each of them. So the conclusion is that we draw from all of this, and that obviously, the smaller particles, they are the easiest to enter the machine, as is already well known. And that the ideal range of this distribution as well, it combines very high impact speed from 250 to 300 meters per second with the angle of incidence also specific, that it tends to be flowing exactly along with the steam. And exactly it will catch there on the edge of the diaphragm block outlet. And it will end up damaging the output. And with that, the process of loss of efficiency is progressive. And a vapor begins to be directed towards an optimum point, not so great, which won't match the read profile. Then you start to have a multitude of other problems, but clearly also larger particles. They tend to damage the coating more. They're from those in this region, from those pieces, when there is obviously some type of coating material. The larger the solid body, the more it will damage the surface of this material. In these cases, the only solution will be right there. It must be contained there in the filter to prevent further damage. So I think that's it for today's video. We covered a lot of it in a very interesting way. Leave your comments and leave your suggestions, your experiences, if you have experienced anything about this. Have you ever designed? Have you ever had any problems, any difficulties? Post here in the comments here. Any photos of any diaphragm block that you have already inspected there in the overhaul, or in the major overhaul of some field inspection or some curiosity. Leave it in the comments too. If you are interested in learning more about steam turbines, I recommend our course. We offer courses in digital, in-person, or remote formats. We go to your company and train your staff individually as well. Or for companies, leave your comments, like. If you liked it, leave a dislike too. Thank you for your attention and company so far. A hug and see you in the next video. I'm gone.